Hello everyone, my name is Joshua Amrit, and today I'm going to be going over molecular docking, a computational approach to protein-protein/ligand interactions. To begin, what is molecular docking? Well, it's a computational method that scores complexes based upon various chemical criteria. The way that it goes about doing this is through the use of employing force fields. Force fields are constituted of different potential energy calculations that are going to contribute to the net potential energy of the complex system. So as you can see, those contributions can include but are not limited to the bond lengths, the bond angles, the dihedral angles, as well as different energy and interaction contributors. So that can be van der Waals interactions or electrostatic energy, solvation free energy. All of those different components are going to get you the net potential energy of the system. It's an iterative process, so once it calculates this energy, it's going to score it and then take the ligand and change some aspect about how it's interacting with the receptor and do it again and give it a different score. And ultimately, you're going to use these scores to help you figure out which complexes would appear to be the most viable given your starting conditions. Molecular docking can fall within two distinct categories, those being rigid body docking, which I'll describe here, and flexible docking, which I'll describe in a moment. Rigid body docking is pretty straightforward in the fact that it utilizes a ligand and it fixes it in space in the fact that it is not able to change any conformational information about itself. What I mean by that is it's limited to 6 degrees of freedom, those being 3 rotational, so rotating along the X, Y, or Z axis, or translating along the X, Y, or Z axis. And so what it will do is, it's an iterative process. It's going to take this ligand, it's going to fix it within the receptor binding pocket that happens to be present. It's going to calculate a score, and then it's going to do it again. Improvements have been made to rigid body docking on the whole, including the use of fast Fourier transform correlations. And this sort of digitized the position of these atoms in space, and so allowed for faster computations. And it's worth noting that this method is just incredibly dependent upon shape complementarity, because it's essentially taking this ligand that's going to be modeled by some space that it's taking up, and the receptor, or at least the active binding site that you're interested in, is going to be treated as a form of negative space. More complex calculations will, of course, include other interactions such as the van der Waals interactions or electrostatic interactions and how that can contribute towards the net energy of the system. But most importantly, it's about how the shape of the ligand fits into the receptor. So as you can imagine, rigid body docking seems to be very, very effective at looking at bound complexes compared to unbound complexes. Flexible docking, on the other hand, allows for the ligand to experience conformational variation, in which the ligand is allowed for different atoms and different groups within the ligand itself to rotate freely so that it can better fit the receptor. And of course, this allows it to be more in line with the induced fit model that we're familiar with within biochemistry. The model itself is typically more computationally expensive compared to rigid body docking, and you can probably imagine that instead of taking a shape and just forcing it into a receptor binding pocket, it's now going to try and explore all of those additional degrees of freedom that the ligand will have access to so that it can better fit the receptor itself. Major strategies that are used for flexible docking include Monte Carlo methods, in which you're essentially looking at the conformational changes of the ligand in a stepwise manner along the potential energy gradient that exists for the complex itself, as well as in-site combinatorial searches, ligand buildup, and site mapping and fragment assembly. About those last two, something that I thought was quite interesting about them was, instead of taking the ligand and, again, conforming it to fit the receptor, it's instead going to take components of the ligand and figure out which of those have the most efficient interactions with the receptor binding pocket in the different sort of ways, and then it's going to reconstruct the ligand from there. And so it kind of works in a backwards direction to what you would expect for this docking protocol. So I thought that was quite interesting. Of course, you're going to also have lots of different docking options, and it's going to depend on which docking you want to perform. So there's rigid body docking and flexible docking, as I mentioned before. With rigid body docking, a lot of those options are going to be computationally cheaper compared to the flexible docking, in that they have a lot in common, especially in terms of the force fields that they'll typically use. You can see that they have variations based on the energy contributions that they have or don't have. And they can be much faster or much slower than each other, again, based on whether or not they choose to simplify those force fields or not. Similarly, with flexible docking, what makes them different is the actual method that they apply for when they're going to perform their calculation. So whether they use Monte Carlo methods, whether they use those ligand fragmentation methods. Some of them also utilize Swarm AI. All of that contributes to the different docking software that's available to you. I want to make a couple different notes. One, the software is very particular based on the complex that you're using, so that's going to be a factor in terms of determining whether or not you want to utilize that software for your complex or not. In addition to this, there are free softwares that are online, or rather servers that are online that you could use. Autodock is one that I've seen. It's not a server; it's a software, but it does seem to be pretty accessible. In terms of rigid body docking, ClusPro has a server. I believe Haddock has a server as well, so that you can submit your structures to these servers and it will perform the docking protocols for you. It'll take away some of the modularity that you could probably have, but it still is a nice option. Finally, I wanted to look at these docking protocols in action, just a brief sort of look at how these can be utilized in an experiment. So in my undergraduate experience, I wanted to look at the interaction between mitonite and anamorphin. As you can see on the left, I first drew up structures that were based off of what I found on the protein database, which is a wonderful tool to use in conjunction with molecular docking experiments. But after I did that, I submitted these two structures that I worked up and optimized to the best of my ability and submitted them to the ClusPro server. And as you can see, it was able to come up with shape complementarity models for those two proteins, as well as electrostatic interactions that could facilitate their complex formation as well. I tried to make some additions towards the image so that you can see the interaction between the spherical shape model and the cartoon model, so that you can see where certain things are interacting with what. But on the whole, I figured it was an extremely interesting in silico experiment to perform. With that concludes my presentation, so I want to thank you for watching. This is my first video on here, I guess, so don't forget to leave a like, comment, and subscribe, and hit that notification bell, because the more views this get, maybe I'll do more. Thank you.